Let's go back to what we discussed last time. So as you remember, I started during the first lecture from introducing different techniques that allow us to do three-dimensional non-destructive optical imaging of director field configurations, and also control of those configurations by means of magnetic and optical tweezers. And so one of the structures that we discussed last time was the structure we call torons, or also the structures of Hopfians that can be accompanied by different types of topological defects, either point defects or little half-integer disclination loops. I demonstrated that we can control the different types of structures we generate in liquid crystals using laser beams by controlling the topological charge of optical vortices. We discussed why those are stable, and we also discussed how we can generate the structures that are pinned in different locations of the sample, or the ones that can undergo Brownian motions and essentially behave like quasi-particles. And so we saw that by controlling applied voltage to those samples, we could have them self-assemble into a number of different lattices. Those would include hexagonal lattices with different periodicity, as well as different chains of such structures, right? So we could control self-assembly of those topologically protected toron and Hopfian structures, as well as topological defects, into different types of arrays when they are not annihilating but rather stabilized in those self-assembled structures. And so what I would like to discuss next is how we can use different types of periodic arrays of such topological defect structures for generation of topological defects in laser beams of light, right? So we can generate periodic arrays of such structures. In here we have square periodic and hexagonal lattices, and in this case, to generate them, we use somewhat higher laser power, so that location of the torons in this case is pinned exactly in places where we focus laser beam. So obviously, as you would now use such a periodic array as a diffraction grating, you could obtain far-field diffraction patterns such as the ones you see here on the slide. Not only that, you could apply voltage again to the sample. Say if you have a material with positive dielectric anisotropy, you could then at some voltage unwind this structure, right? And so fully erase this periodic array of toron structures, so that you essentially erase the diffraction grating. Then later you could generate a different one. Say if initially you had a hexagonal lattice, you could then generate a square periodic. So those diffraction gratings are optically reconfigurable, and we can control the diffraction patterns by applying voltage. We could also generate a number of quasi-arrays. So here you can see a quasicrystal-like pattern, honeycomb lattice, and remember that each of those little tiny structures that you see in those pictures corresponds to double twist torus with a pair of point defects that we discussed in details last time. So now if you generate such a periodic array that has a dislocation in it, right? So in here you can see such a dislocation, because if you were to count the number of rows of torons on the left side and right side, you would get a different number, right? So there is a dislocation with Burgers factor equal to this periodicity. You would then be able to use it as a diffraction grating again, but after looking carefully at what you get in the diffraction pattern, you would notice that all the laser beams in the first diffraction order in here would have dark spots in the center. This is already indicative that what we got are optical vortices, right? So indeed, if we were now to take one of them and study the optical phase profile that we have in this case, you would note that all of those laser beams have a phase singularity in them, and this is the reason why the intensity of laser light goes to zero in the very center of such diffraction, first diffraction order beams in here. Right, so we have phase singularities, that means we have optical vortices that are generated by arrays of topological defects with a dislocation in the array. Right, so now if we would go to the second order, we would note that we have more than just elementary screw dislocation in phase of light, right? The Burgers vector of those dislocation is increasing. And so you can see that we can also control the charge of the optical vortex that we generate. You have a question, yeah?
In this case, the optical vortex is only due to the dislocation in the lattice, right?
That's correct.
The shape of the, I mean, the fact that we have a toron doesn't play a role.
Yeah, this is a good point. We could also have a refractive index contrast due to some other reasons. For example, we could assemble an array of colloidal particles that would give us refractive index contrast between particle and the surrounding medium, and in that case we would still have an optical vortex in the diffracted laser light, right, in the first order in here. But what is interesting here is that we have defects at all different levels, right? Because the array is composed from defects. Then we have a defect in the array, which is this dislocation, right? An edge dislocation. And then we get a screw dislocation in the phase of light that we diffract, right? So it's all about defects in different levels of the soft matter system in here, and also in the phase of light that we get. So I think it would be possible to do it with just colloidal particles, for example, but it's more interesting to be able to do it with, quasi-particles, which are here formed by torons that have point defects and this Hopf vibration in them. Okay, but very good question. So in order to be able to study the phase profiles like the ones you see in here, we used the Stokes polarimetry setup that you can see presented in here, where a helium laser beam is split into two, and one of them only is going through the sample, but then the two are recombined, and by rotating the polarizer and also the quarter wave plates in here, we can study intensity patterns here using CCD camera detector. We can study intensity as a function of different angles of the quarter wave plate and polarizer, which then allows us to find the Stokes parameters. In particular, we need S2 and S3, and those are found, as you can see, by simply using intensity patterns that we detect using the CCD camera. And then we can find the phase profile, the one that I showed you plotted on the previous slide, based on the Stokes parameters S2 and S3 that we find this way for the detected pattern obtained using this CCD camera. Okay, so this is detail that I thought would be useful for you to know how we do it. And now we have a clicker question. So you remember we had Robin talking to you a little bit about dislocations in the past. And here you saw some dislocations. Let's see if everybody clearly understands what dislocations are. So the system is on. We need more volts. I hope you have your clickers. Do not forget them in the dorms. Alright, I'll stop the system. Okay, let me see what we get. Majority got the correct answer. Very good. So, as you could also see, those defects don't have to be in crystal, so liquid crystal. They can also be in phase of light, right? We actually had a screw dislocation in the phase of light, forming the optical vortex as well. So correct. So now you can see we can also generate a number of other patterns. And so here you see a hexagonal lattice with the 5-7 pair of defects. And so in here in the very center. And again, those kind of gratings can be controlled by voltage. You can see quite substantial change in the contrast as we apply, a voltage of less than 1 volt to this liquid crystal. Again, we can obtain a diffraction pattern and study what we have in the first order diffraction beams, and we can see that they have different phase profiles. So it's interesting that again we can obtain different defects in periodic arrays of torons and then use them to obtain different types of singularities in the laser beams of light that are used to obtain diffraction gratings, and those results very nicely agree with simple computer simulations that we do as well. So again, reminding you that every single dot in those large arrays corresponds to an elaborate toron structure that we generate also using optical vortices. Right? Okay, so now next I would like to discuss not only the toron and Hopfian structures, and you could see how we can use them to form different types of periodic arrays with or without defects, but also two-dimensional structures of solitons, right? So torons and Hopfians were examples of twisted solitons, but we could also have two-dimensional versions, and those have analogy with the so-called baby Skyrmions, two-dimensional baby Skyrmions, or simply two-dimensional Skyrmions that are also found in ferromagnets, chiral ferromagnets. And so although the texture of magnetization in this case, for example, is changing continuously, the structures, and then you can see here, they have the form of double twist cylinders, similar to what we saw, we also have in blue phases, right? So those structures are topologically protected because if you have two-dimensional system, one of such structure cannot be easily unbound through uniform smooth deformations. And also, you can note that in such a structure, you have all possible orientations of quantization. So if you were to map the field configuration you have in here onto the unit sphere, you would fully cover the sphere. So they have properties similar to topological defects, and this makes them very interesting. They can also be characterized by the so-called Skyrmion number, because in addition to just Skyrmions with which cover the unit sphere once, you could also have structures that would cover it twice, like the one you can see depicted in here. And so this one has Skyrmion number 2, and so on. And in addition to such structures, one can realize many others. So again, in chiral ferromagnet community, they came up with lots of names for those structures. So for example, the one you see in here is called Bimerons. So what we have in here is essentially 2 half disks of such Skyrmions which are connected by a twist wall, essentially. Right? And so what I would like to demonstrate to you next is that in liquid crystals we can also realize analogs of such structures. So in liquid crystals there are many ways of forming defects, especially if you have a chiral, nematic, or cholesteric liquid crystal. And so some of them would have non-singular nature, and the others would have singular nature. So let me demonstrate what I mean by this by showing the 2 examples in here of half integer disclinations, -1/2, each of them. But one of them here on the left is called lambda disclination, and the director field in the very center of singularity is along the defect line. So you can imagine that for this reason such a disclination will not be very energetically costly, because you do not need to melt liquid crystal to an isotropic state in this defect core. Right? While the other example I'm showing here, which is tau disclination, has a singularity in the material director field. So this means you would actually have to either melt this core of disclination or form a biaxial core in order to be able to reduce free energy as much as possible, and avoid divergence of free energy. So 2 more examples in here involve the +1/2 analogs of those disclinations, so tau +1/2 and -1/2. So by looking at those lambda disclinations in here and in here, you can note that pretty much everywhere we have uniform twist of director around such a disclination, and we don't have a singular core. So such defects are not very energetically costly, and we can expect that they will be quite abundant in cholesteric crystals, which is indeed the case, as we will see in just a minute. Right, then we additionally can have double twist cylinders, or they can be also classified as lambda +1 disclinations, non-singular. Right? So that would be a direct analog of that, of the baby Skyrmion that we just discussed. We can also have -1 disclinations, right, like the one in here, also twist escape. In addition, we can have the twist disclination, such as the one you can see in here, in which case you can visualize the director around the disclination as being tangent to a Mobius strip, as depicted in here. Right? And those can also be quite frequent in liquid crystals. And so next, I would like to demonstrate a series of structures that we can generate in confined chiral nematic liquid crystals, again using different types of laser beams, just by controlling slight, tiny details of generation, such as laser power, whether we use electrodes with we use confining glass plates with transparent electrodes or not, because that will influence heating of the sample and so on. So one of the structures that we can generate is very much analogous to the baby Skyrmion or two-dimensional Skyrmion that I showed you we can form in ferromagnets. So in here we essentially have a double twist cylinder that's perpendicular to the walls of liquid crystal cell with perpendicular boundary conditions. And then close to the substrates we have two disclination loops, which are twist disclinations in both cases, right? So if you would look in the middle of the cell, all we have is essentially pi twist in all radial directions, just like what we have in the case of twist Skyrmion in some of the ferromagnetic systems, the chiral ferromagnets. But what's different and also interesting is that the interaction of such a double twist cylinder structure with perpendicular surface boundary conditions results in the formation of two loops of the twist disclinations at the top and bottom substrates of the liquid crystal cell. Right, so in a sense, you introduce this double twist cylinder in, major fraction of the liquid crystal cell here, but close to substrates, you terminate this twist by introducing loops. So this red line in here is a loop formed by such twist disclination, right? Yeah.
Excuse me, maybe you said this, but I missed it. What are the theoretical pictures that we're looking at? Are those analysis of data, or are they conceptual, or are they minimizing the free energy?
They are experimental data. So essentially, based on images of this kind, many images of this kind, you can reconstruct what happens with director field, say in the middle of the plane, and then because we have resolution not only in the plane of the sample but also across the sample thickness, you can probe what happens with director field as you come close to substrate. And so you can note that we do meet the surface boundary conditions, right? And that happens because of presence of those disclination loops.
Excellent, thank you.
Yeah, thanks. All right, so in a sense, as I already mentioned, in order to terminate this double twist cylinder at the substrate with perpendicular surface boundary conditions, we need to have such a loop of twist disclination close to it. So next I would like to show a series of other solitonic localized structures that have translationally invariant configurations. And so in here you can see an example where again in a chiral nematic with initially unbound uniform state with satisfying perpendicular boundary conditions, we can generate such a structure by simply dragging the laser beam in the liquid crystal at certain speed. And so as we do it, we can generate two structures. One of them in this location is called cholesteric finger of the first type. And in a sense what we have in here is a quadruple of non-singular lambda disclinations, right? Minus lambda minus 1 over 2, 2 of them here and here, and lambda plus 1 over 2, right? So those are disclinations which are non-singular in nature, so they don't cost much energy, but in here they allow us to introduce cholesteric twist in an initially unwound frustrated cholesteric cell, right? So by laser light you can relieve this frustration. The material wants to form a twisted configuration, but the boundary conditions don't let to do it, and so initial black and here unbound homotropic state is not necessarily energetically favorable, but by shining the laser light, we can relieve this frustration locally and draw such defect configurations, right? So in here, this is a quadruple of disclinations. Now, in this location, you can see that the appearance of the line changed somewhat, and it's different. And so what this fragment of the line corresponds to is a structure of cholesteric finger of second kind, where we have 2 minus 1/2 lambda disclinations and 1 plus 1 disclination, right? So again, in both cases, we have conservation of the winding number of those disclinations, and they allow us to introduce locally cholesteric twist in an initially unwound system, right? So now we can generate a number of different configurations, obviously, by using scanned laser beams. And now what they're showing here is a cross-section of such a structure that is obtained by Paul through minimization of Frank-Ozen elastic free energy, and you can see the details of directed field corresponding to it. The previous ones were all reconstructed from experiments. Now, using this type of directed field configuration in the cross-section, we can computer simulate the polarizing microscopy textures, and we can see them, having similar appearance, although many things could appear like this, right? So it's good to see the qualitative agreement, but just that wouldn't be sufficient to prove this is exactly what we have in the sample. However, it's good that we were able to reconstruct also similar field configuration from experiments. Now, we could also computer simulate the vertical cross-section image, and so in here this is done, just showing by different colors of light, gray and green. Green is experiment, and again you can see qualitative agreement over cross-section corresponding of the sample obtained in 3-photon excitation fluorescence polarizing microscopy. So again, there is a good agreement between experiment and the modeling. Likewise, we can do it for the second structure of cholesteric finger second time. So you can see the appearance and polarizing microscopy texture is slightly different. It now became asymmetric, right? And so again, we can computer simulate vertical cross sections. They too are now resembling each other but different from what we had for the previous structure. And so this shows that we indeed deal with those particular director field configurations that I showed on the previous slides. All right, so let me give you a couple other examples of how sophisticated two-dimensional patterns of such quadruples of defect lines we can generate, right? So, for example, on the cover of this one of mathematics textbooks is a cat that we could reconstruct by generating topological defects in confined cholesteric liquid crystal sample, right? So we can generate all kinds of diffraction gratings and spirals. And the whole reason we can do all of this is because the defects, which are non-singular lambda disclinations in all of those cases, allow us to locally introduce cholesteric twist in a system which would like to form twisted structures, but is prevented from doing this due to confinement and boundary conditions, right? So introducing twist with helical axis in here being tilted allows to locally minimize energy and form those long-term stable structures. Right? So now let me demonstrate that we can use them to generate optical vortices as well. Right? So in here we generated a linear grating formed by cholesteric fingers of the first type, and we now note the dislocation, edge dislocation in here in this grating. Right? Now if we shine a laser beam of light, we obtain such a diffraction pattern, and so you can note that already in first order diffraction beams we see those dark spots, right, which are indicative of us having phase singularities, and as you go to higher order beams those spots increase in size. And indeed we can study the phase profile of those diffracted laser beams and note that indeed in here we have elementary Burgers vector dislocation. So the charge of optical vortices in those two laser beams of the first order would be plus minus 1. If we then instead introduce a Burgers vector, introduce an edge dislocation of larger Burgers vector, we can see that no, project seems to be working. We then note that we already have, already in the first order, we have screw dislocation, the net total Burgers vector screw dislocation is twice as large, right? So we don't have just one elementary dislocation. And so the charge of the phase singularity in those first order beams would be plus minus 1. Right? So we can this way establish a simple relation between the Burgers vector of the dislocation we work with and the number of diffraction order as well as the charge of the optical vortex that we obtain. And so it's important also to note that when we generate those large, when we generate the optical vortices with large charge, like 2 in here, oftentimes they tend to split, right? So we don't have a screw dislocation of Burgers vector 2 of the periodicity, but we have 2 elementary vortices. And it's interesting that this is analogous to what we observe in liquid crystals, where the defect lines with high strengths tend to split into defect lines with elementary winding number or strengths. But here this is because of different reasons, right? It's not because of energetic reasons, but because of the presence of coherent background in the screw dislocation, the dislocated waves. So now one can generate a number of other different patterns and use it to obtain phase singularities in the diffracted laser beams. So here are some more examples. So for example, when you generate edge dislocations with the same orientation of Burgers vector of those elementary edge dislocations, then the optical vortices that we would obtain would be rotating as a function of distance from the diffraction grating to the location in which you detect it. And in here you can see that the measured angle is actually in a good agreement with theoretical predictions that one would expect for this case, right? So this in principle could be used to measure distance in certain cases. All right, so yet another example of the elementary dislocations with opposite orientations of Burgers vector in here, and this allows us to obtain interlinked edge and screw dislocations in the diffracted laser beams when we use this kind of pattern as a diffraction gradient. Right, so you can see from those examples that the patterning of defects, in this case defect lines in the confined cholesteric liquid crystals, allows us to control the details of phase singularities that we have in diffracted laser beam supply. And just like before for the patterns of defects that we obtained for the case of torons, in here too we can control them by applying voltage. So again, what you see in those series of images here is that applying voltages of the order of 1 volt or so, we can fully erase those defects and then draw some other different gradient, right? So they are again optically reconfigurable, and we can control also intensity of different diffraction orders. So those are examples in here of diffraction patterns that change as you apply voltage, and you can see how the different minima and the intensities of different diffracted order beams, first right and left, second right and left, change as a function of the applied voltage. So now we again, just like before, for the examples of interacting torons in those arrays I demonstrated before, we can generate both torons and those finger configurations in such a way that they are pinned to the diode locations, but also in a way that allows them to interact with each other. And those interactions can lead to different types of self-assemblies, examples of which you can see here. And so now I have a question to you. Why do those interactions and self-assembly occur? What are the physical mechanisms? That lead to this behavior? So perhaps you could think about the answer based on the other examples we discussed for self-assembly of torons in applied fields, and what were the reasons we were able to have this self-assembly and control it. All right, I'll stop the system because I seem not everybody voted yet, but we need to cover still a lot of material. So let's see what we have. Majority answer B, and that's the correct answer. Those are elastic forces that originate due to direct field configurations around those structures propagating to relatively large distances. So good. Just a couple more examples of how we can pattern those topological defects, not only in two-dimensional arrays, but also into three-dimensional arrays. So in here you can see examples of structures where we have bilayer configurations, right? So if you were to cut such a structure in this particular location, you would see that we have torons in one layer and fingers in the other layer, right? And in here you can see the computer-generated field configuration corresponding to such a cross-sectional image where we have toron, it's axially symmetric in here, and translationally invariant fingers perpendicular to the screen. Right, so in here it's another example where we have just arrays of fingers and in two bilayer structures. Again, those correspond to different orientations of cholesteric fingers of the first kind, where the helical axes are tilted in opposite directions. So those types of structures in here were obtained in polymerizable liquid crystals, and so we can cross-link them as well, and you could obtain solid films from such polymerizable liquid crystal in which it generates such structures. Right? Now, you can note from this video that both torons and the cholesteric fingers we have in here can be controlled dynamically too, right? So if we, for example, in this particular case have scanned laser beams, we can control dynamics of such structures. Right? This is what I wanted to present on the solitonic field configurations and optical generation of defects in liquid crystals, as well as their use for generation of phase singularities in laser beams of light. Before switching to the next part of my lecture, maybe I can answer questions if there are some. Or we could ask them in the very end.
The three-dimensional structures, what size is possible in the experiment?
So everything here is dependent on cholesteric pitch, and in principle you could have liquid crystals with cholesteric pitch as short as 100 nanometers, and you can go all the way to hundreds of micrometers. There are some experimental challenges on the short length scale and longer length scales, but anywhere between 3 to 100 micrometer we are able to do quite easily. Okay, so the next part of my talk is related to the topic that was already also covered by Uroš Tkalec in his first lecture. So it will involve colloidal particles that are introduced into liquid crystal, and as you remember from his talk, it is possible to control the surface boundary conditions on the surface of those particles to be tangential or perpendicular. In my talk, I will try to present non-spherical colloids, topologically complicated colloids, and how the geometry and topology of those colloidal particles is influencing the types of defects that we can generate in liquid crystals. And before I do it, I would like to remind you some of the theorems that you have been introduced to already a couple times, I believe. One of them by Robin, and I believe I myself already mentioned some of them too. And so the first is this theorem, Bold theorem, which tells us that you cannot comb hair on a spherical particle or vector field. You inevitably will have defects in this field on the surface of the particle. And so indeed you can see that as you try to comb it to be uniform on one side, by the time you turn to the other side, you get a topological defect, right? And so now an extension of this theorem, which is called Poincare-Hopf theorem, says that that this is also true, can be extended to surfaces with other genus or Euler characteristic. And so in general, for all two-dimensional surfaces, one will have to have the defects of net winding number equal to chi, where chi is nothing else but 2 minus 2g, and g is the genus of the surface. So in here you can see what we should expect for different surfaces with different numbers of poles. For example, for torus, we don't have to introduce defects. We could actually be able to deal with the uniform vector field or director field. While if you go to higher genus surfaces, then the net winding number of defects should be equal to chi. So we can see now and understand how those theorems nicely work for colloidal particles in liquid crystals. Right? So here is a spherical particle inside of a nematic liquid crystal where we have tangential boundary conditions, and we see that liquid crystal just nicely visualizes for us how this theorem should work, because indeed we note two Bourgeons on the surface of the particle, and as we would look carefully at what winding numbers those two-dimensional defects in here have, we would realize they are both +1, and so indeed the Euler characteristic of the sphere is 2, so that would add to chi, right, to 2. Now this is also easy to see that if we have particles with perpendicular boundary conditions, then we would introduce the net charge of defects in the bulk charge, Hedgehog charge of defects to be 1, because the particle itself is similar. If you look at the director field around its surface, it's similar to that of a hedgehog, radial hedgehog point defect, and so then another point defect has to appear to make the system, the charge of the system equal to 0. I would like to start from still an example involving spherical particles, but demonstrate that we can have some interesting examples that go beyond those two classical examples I already presented for you, right? So if you note that the particle with tangential boundary conditions does not induce bulk defects at all, right? While the particle with perpendicular boundary conditions induces bulk point defect or a disclination loop of half-integer strengths, which is topological equivalent to bulk point defect, right? And so the question is, could we have, for example, a case of particle with tangential boundary conditions that would, however, have non-zero bulk, induced non-zero charge of bulk defect. And so this is indeed possible, but we were able to observe such situations so far only in chiral nematic liquid crystals. So here is a liquid crystal cell where we have initially fully unbound director field, which is perpendicular to the image of the picture, and this is observation between cross polarizers. And we can note that in this system, we can generate those torons that we discussed with you earlier today. And next to here, right, so here is an example of toron. This is how it looks like between cross polarizers, the structure that you are quite familiar with already. Now, next to it in here is a particle with tangential boundary conditions, and it has two Bourgeons, one above the particle, one below the particle, across the sample thickness. Now, it is important to note, right, that this example of particles to bosoms is satisfying the mathematical theorems for what we expect for the net charge or winding number of defects on the surface of the particle. But the charge of the defect of the particle as a bulk Hedgehog charge is equal to 0, right? Because it's embeddable easily in uniform director field, we only have surface point defects. So now, however, those two other structures, we have question marks next to them because they are different. You can see already from the appearance and the cross polarizers in an optical microscopy that there is something different going there. And we can take cross-sectional images, right, of such structures that are depicted in here, and you can see that cross-sectional views of those are quite a bit different from each other and also from what we would expect for particles with just bosoms generated next to them. So together with collaborators from Ljubljana in Slovenia, we were able not only to reconstruct director fields but also to analyze the structures that we obtain in all of those possible cases here. Right, so it turns out that the colloidal particles in this case are accompanied by the double twist, a loop of double twist cylinder or double twist torus, and so they're essentially dressed by such double twist torus, which appears asymmetrically with respect to the liquid crystal cell thickness, right? So the particle is kind of pushed to one side, and the double twist torus is roughly in the middle of the cell, but then we have a hedgehog point defect, the hyperbolic point defect here on the other side. And so if we now map what is happening on the surface of the colloidal particle, we know that the director field configuration is quite a bit different, right? Because we essentially have this kind of splay configuration where the director is undergoing this fairly complicated configuration here. And what you also want to note now is that because the topological hedgehog charge that would correspond to the loop of double twist torus, or cylinder or double twist torus, is equal to 0, that means that because we have this hyperbolic point defect, the bulk charge of this sphere with such a pattern of director field should be non-zero, right, and should compensate for the charge of this point defect in here. Now, in the other case that we demonstrated in here, right, this is a cross-section, we can again reconstruct director field, and we again have a loop of double twist torus, double twist cylinder or double twist torus, and we don't have bulk point defects anymore, only bosoms here and here. And if we plot the director field on the surface of such a particle, as well as then map it to the order parameter space, we realize that the bulk charge is 0 now, and this is consistent with the fact that we don't have bulk point defects anymore. And you remember also that the hedgehog charge of the loop of double twist cylinder is also equal to 0. So this means that the colloidal particles with tangential boundary conditions can acquire non-zero charge as well, just like the ones with perpendicular boundary conditions, if we make some complicated patterns of field configurations now on them. and those charges can alternate between 0 and 1. So this is an example of what we can obtain in chiral nematics for particles with tangential boundary conditions, but equally interestingly, similar combinations of solitonic twisted field configurations and colloids can also occur for the case of perpendicular boundary conditions. So what you see in here is again a chiral nematic liquid crystal which is confined into a salvage perpendicular boundary conditions. And so now we have, however, a particle with perpendicular surface anchoring. And so we again generate this solitonic structure, which is essentially a loop of double twist cylinder, and this can be seen both in experiments. This is a cross-sectional image, and also in numerical modeling. And then we have a loop or point defect or loop on the other side of the cell. So again, the net topological hedgehog charge corresponding to a loop of such double twist cylinders, this is essentially what this is, it's homomorphic to it, is equal to 0. So this defect loop of half integer disclination here is essentially compensating the hedgehog charge of this colloidal sphere with perpendicular boundary conditions. So you can see that in chiral nematics, a lot more of interesting configurations can occur compared to just nematics, because we can have also those twisted solitonic structures occurring in combination with colloidal particles. But what I would like to discuss next is how we can use colloids with non-spherical geometry and also different topology than that of spheres to generate even more interesting types of defects in liquid crystals. And so to be able to obtain such particles with pretty much arbitrary shapes, we use the technique of two-photon photopolymerization, which is very roughly schematically shown in here. What we have is a femtosecond laser source, and we focus it tightly by using high numerical aperture objective, and then we can control the sample or objective by using a nanostage which controls XYZ positions with nanometer precision, so that we can draw, we can polymerize colloidal particles of any desired shape. Right? So this happens because we initiate the polymerization by means of two-photon absorption. Right? So photoinitiators are essentially dyes, and they can be activated not only by means of single photon absorption, but also two-photon absorption. And so as we do it, we cross-link the material, essentially converted from fluid to solid in the desired location, and then we scan the laser beam through the sample by drawing any structures we want. Right? And so an example you can see here. So this is a computer model that we built to generate a particle which is shown in the bottom in here. And so as you can see, the particles can be with the size of the order of micrometers. So that means you can generate colloidal particles that would undergo Brownian motion and have all properties of colloids of interest to us. What this technique is that I just demonstrated is essentially a very high-tech version of 3D printer. It allows you to do the same, print 3D objects, but with resolution which is essentially 100,000 times better than that of commercial 3D printers. Alright, so let us see what types of colloidal particles we can generate. And so the first example I would like to discuss is the spiral-shaped particles on which we can induce perpendicular surface boundary conditions. And so then what we obtain is spiraling defect configurations, so which are depicted in here. And you can understand what happens in here by simply, keeping in mind that such a spiral object is still homeomorphic to sphere. So what essentially happened is you morphed the sphere to a spiral, but also this defect loop, the Saturn ring that we had for spherical colloidal particle, got morphed to a spiraling defect loop that you can see depicted in here by this bluish line. Right? So, well, geometrically it's interesting, but topology is the same as we had in the case of spheres, because those two are homomorphic to each other. So I think I will need to stop at some point now and just simply tell you that during the next lecture we will go beyond the particles that are homomorphic to spheres. We'll discuss colloids such as the ones that have non-zero genus, different numbers of poles, and also colloids that have shapes with in the form of nodes and links and so on. But now I would like to answer questions that you might have. Thank you.